Alright guys, these videos are for in-house training of our instructors. You can use these in your class if you need to, but obviously not as a replacement for teaching the topic, but if you need to show something on the screen. But you can't put any of this online. These labs are proprietary to LabVault. As I'm doing these labs, you'll see that I'm using the units with the metal around the outside. Students should be using these guys here, the shrouded leads, as we go forwards, okay? So these ones will be able to go into the terminals there. I'm simply using the metal connections just so that I don't steal too many from the advanced lab. So the first page, if we're looking at the procedural outline, this is in the instructor's manual on page 2. And I believe, let's see, what page is this on the student manual? This is also on page 2 in the student manual. So the first thing they're having us do is just look at voltages. So the connection on the back here is the same twist lock cable that you're going to see for the RLC trainers for the LabVault units. So you can see here that they're a twist lock connector with 3-phase, and they have the center tap there for the 120. So you can remove, we'll most likely have new cables available just for these trainers, but in the meantime you can disconnect the RLC trainer and then connect up the transformer trainer. So just make sure she's on, beautiful. Okay. One issue is that I found, we'll have to see if there's a way that we can lock this off while they're working through their projects there. But the first thing they're asking us to do is just check on the voltages between the terminals and then have the lamps light up, right? So they want 120, so between any line and the neutral, so they're measuring the voltage and then connecting up the lamps across a line and a neutral connection. And then they're also connecting up between line to line. So obviously we'll just set up one of these guys to look at, like, we're not going to check every phase here, right? But we'll just check out the phases here, right? So we'll go A to B, and when we turn it on, then we can see that obviously one, what's going on there? How come that first one's not working? Is that tied together? Help if I read the manual, okay? There we go. Okay, donkey. So it looks like we have to make sure that that connection is made there. So there is this connection here on the neutral. I thought it was tied in together, but you have to tie that neutral in there. Okay, then obviously you're going to see your fully bright and your dim lamps there. Okay, let's grab a meter. We'll look at the voltages there. So again, these jumpers that we're using can go straight into the meter. So we'll put our voltmeter there. Can you guys see that? Yep. Okay, and then we're just going to connect up between the two terminals there, and we should see the 120 and the 208. Okay. Depending on the voltages, you may want to get your students to wear the high voltage gloves. But the way that we're hooking these guys up, we are not putting ourselves into the circuit. We're not even holding the meter leads. So you may not need to use those high voltage gloves as long as you're doing like this, where you've got it set up. Then you take your voltage reading, right? So there we go. So we can see there that we got 119.8 volts on the dim light there, between line and neutral. And then obviously between the two lines, then, apologies if this is just super simple for you. Just making sure that everything's cool. And obviously, like a donkey, I didn't know that that jumper needed to be there, right? So maybe there's a reason for why we're doing this video. So this one's 2.8, 2.9 volts on the bright bulb. Sweet. So now we know the voltages between the line to line and line to neutral, and get the students to test out between A and B, B and C, C and A, and then from each subsequent A to neutral, B to neutral, C to neutral, and make sure everything's cool and the same voltages all the way through. Just keeping an eye on them and making sure that every time that they change their connections, that they are disconnecting the voltage to the transformer trainer.
Okay, so that takes care of this page where we've taken the line to neutral and line to line voltages. They can put them in here and they can show the brightness of the lamps there. Then the next one it says on distribution, let's make this a little bit bigger here. So on distribution transformer, according to industry standards, H1 and X1 have the same polarity. So I usually note that with, let's get some color going here. So dots on each one to denote their polarity. A transformer is said to have additive polarity when the bushings H1 and X1 are opposed opposite to each other. Similarly, the transformer has subtractive polarity when H1 is adjacent to X1. So let's take a look at the additive first. So the one on the left there. Okay, so we've got our additive connection there. It looks like we have the H1 and H2, and what voltage is being applied. So we got 24 volts that's being applied there. Okay, so we got 24 volts on this guy. Okay, and then looks like H2 is then tied in with X1. So we'll just do the next winding. I like to draw them where they're side by each. Okay, so there we've got X1, X2, and X3. So throw in H1, H2, come on, X1, X2, and X3. Okay, and it says that it's a 2-to-1 ratio, right? So that means that these guys are going to be 12 volts each. Okay, and we've got a jumper between the primary and the secondary there. Okay, so we have the jumper right there. Okay, I usually draw arrows going like in this polarity. So we got H1 to H2. Then I've got these two magnetic fields are going to set up here. And then I usually just draw the additive voltage in that we have from here to the other side of the circuit. Okay, so that's looking at this voltage right here, right? So we have the jumper being denoted right here in the green, and we've got our voltage being read, and it says it's going to read 36 volts. So obviously we've got the 24 volts, right? Plus another 12 volts. Hang on, what's going on there? Oh, so I've already screwed this up. So I misread this. It's a 2-to-1 ratio, and when 24 volts is available there, then there's 12 volts across everything. Okay, so sorry about that. So these guys must be 6 volts each. Okay, giving us 12 volts. So then we've got our 24 volts plus our 12 volts, giving us 36 volts as our additive polarity voltage. Okay, sweet. Okay, then for the subtractive voltage, so I know it's all here. I just like to show it in a line there. So it looks like we're going to have a jumper between H2 and X3. So that the secondary of the transformer has now been flipped. And then for the voltage is again going to be placed here, but the voltage is now going to be between H1 and X1. Okay, so we've got our primary here, H1 and H2, and then we've got the transformer. And I usually just draw it the same as I did before, and then I show that the connections are onto a different spot there. Okay, so we got X1, X2, and X3. We've got our magnetic fields that will set up like this. This one was 24 volts, right? This is 6 volts and 6 volts, summing to give us 12. And then the jumper is now in a different spot, right? It's going from H2 to X3. So we're going from H2 and we're going over here and we're going over to this side of the secondary winding there. Okay, and then the voltage is being taken between H1 and X1. Okay, so voltage is going to be here between H1 and X1. Okay, so here we've got obviously 24 volts, right? So we're going through this winding here, then we're going in the opposite direction through the 12 volts. So we got 12 volts, 24 volts minus the 12 volts, leaving us with 12 volts for the subtractive polarity, matching with what we have here. Beautiful. So 36 volts was shown for the additive polarity and 12 volts being shown for the subtractive polarity. Okay, again, apologies if this is fairly intuitive. It's just I'm just showing the way that I like to demonstrate the bucking and the boosting there. Okay, I was thinking of adding in the buck boost nodes for the Hammond transformer trainers, but I think that these Festo trainers would be best suited after they finish the Hammond transformer trainers. So the Hammond transformers trainers being those gray boxes. So they would finish those guys off, and then this would be supplemental to what we were using before. Okay, so the next thing they're asking us to do on 3 is on transformer T1 of the distribution transformer trainer. So this was just theory above. Now we're actually going to hook them up. On transformer T1 of the distribution transformer trainer, connect H1 to line A, H2 to line B, interconnect H2 and X1. Okay, so let's do a quick little diagram over here. So we've got our primary here. So that's going to be connected to our voltage source. So line to line, that's going to give us 208 volts there. And then we've got the secondary, where we've got X1, X2, and X3. I believe that's 120 volts across each of those guys. Okay, and then it says, so connect H1 to line A, H2 to line B, and interconnect H2 and X1. Okay, so looks like that's going to be an additive connection there. Okay, these magnetic fields are setting up like this. Okay, then let's see what the next thing is. Turn on the distribution transformer trainer. Determine if the transformer is connected with additive or subtractive polarity by observing the relative brightness of the lamps or by measuring the voltage between terminals H1 and X2. Okay, so the voltage is going to be taken between H1 and X2. Okay, so that should be, in this case, that should be 208 volts plus the 120 volts. So that's going to give us, what, 328? Okay, I believe when I did this, I got 320 volts measured. Okay, so that takes care of this guy. Use 2 lamps in series if you determine the voltage by observing the relative brightness of the lamp. Okay, so the lamps are rated, so the lamps are rated at 240. So if we're reading 328 volts, then between those guys, then the 2 lamps are going to have to be connected in series, right? So if we had 328 volts expected divided by the 2 lamps, that should give us 164 volts across each lamp. Okay, and I have a note here that I measured 159 volts across them. Okay, repeat your observation on transformer T4. Calculate the expected voltage between H1 and X2 if the voltage applied to H1 and H2 is doubled. Okay, that one I got a different answer. So that's the same diagram there. So it says calculate the expected voltage between H1 and X2 if the voltage applied to H1 and H2 is doubled. Okay, let's find a different color here. So if we did that, then we would have 416 volts, right? Then we would have 240 volts across each of the windings there, right? And if we were, so quick diagram here. So we're taking our voltage between this guy and this guy, right? So that would be the, 416 plus 240 volts, right? So that would be, 656. So that's the question that I have, because in the answers there, they give you 624 volts. So maybe I made a mistake there. I'm not sure what I'm missing there. I don't know. I don't know where I went off there. So you guys can tell me what the issue is and what I've missed on that point there. Okay, that's pretty good. Let's jump back to the lab and let's take a look at the connections there and see what voltages come up.
All right, guys, on page 4 of both the instructor's manual and the student manual, next thing they're doing is they're checking to see whether it's additive or subtractive polarity. So number 3 at the top of the page says on transformer T1. So let's move this guy over. Of the distribution transformer trainer, connect H1 to line A. Okay, so let's connect H1 to line A. Okay, then it says H2 to line B. Okay, so we're putting 2.8 to the primary of the transformer. Okay, and then it says to connect, what does it say? Interconnect H2 and X1. So we're going to connect H2 and X1 together. And what are we looking at? We're looking at, so it says turn on the distribution transformer trainer, determine if the transformer is connected with additive or subtractive polarity by observing the relative brightness of the lamps or by measuring the voltage between terminals H1 and X2. And you use 2 lamps in series if you determine the voltage by observing the relative brightness of the lamp. So we may not want to work on the wording there. So first thing is we would want to look at the voltage between H1 and X2. So between H1 and X2. Okay. I believe it's additive, but let's see what's going on here. Okay, so we got 329 volts. Okay, so I've got the 2.8 plus the 120, right? So that's going to give me 328, 329. It's supposed to give me 328, but we're seeing 329 on the meter there. Okay, then they want us to connect that across the bulbs. Well, we've got to put the bulbs in series, right? So let's turn this off. So the bulbs are rated for 230, right? And we just saw a disgusting voltage of 328. So we've got to put 2 bulbs in series here. And then we're connecting between those 2 points, right? So we're connecting between H1 to one side of the light. And then we need the other side, what were we looking at? H1 and X2, right? So this side of the lamp is going to go to X2 here. Okay, so that means that we're going to have 328 across each of the, across both lights. So we should have 164 volts across each of them. So interesting to see there that the voltage is dropped by 10 volts there as soon as we put the load in. So you're going to find that the internal resistance of the transformer is going to affect your output voltage there. So we got 318. We had 328. Let's see if we can open up the circuit and see what happens. Right. So there it goes back to 330. Right, and then reconnect, and the voltage drops there. So that might be a good discussion on because they'll be baffled as to why that happens. So we'll see whether we put that into the write-up of the lab or whether you guys are going to go through that on your own. Okay, but obviously we need to work on the write-up in that we should be taking a voltage first, then connecting up the bulbs across that load, because we don't want them to put 328 volts across the lamp, which is only good for 230 volts. So you can see here that you really want to go through this nice and slowly with the students. You want to go through a full lesson with them prior to them sitting at the actual station there. Okay. Next one is it says repeat your observation on transformer T4. Okay. Well, we can do that just by transferring those jumpers over there. I guess that's just to show that they are the same, but let's see if there's any difference between them. So all I'm doing is just transferring those terminals over. They have the identical terminal markings on the transformer. Okay, so there's our 318 again, two dim bulbs there. And then if we open up the circuit, then it's going to go to 330, 328. Excellent. Okay, so that right up in the middle of page 4, saying that trainers built with transformers having their primary winding rated at 2.8, that's pretty much for the next question there on number 4, single-phase transformer supplying single-phase loads. When connecting the primary winding of one of the trainer transformers between lines A and B, the rated voltage is applied. That's 2.8 volts. When the same winding is connected between lines A and neutral, only 120 volts is applied to the primary winding. In this particular case, what's the percentage of the full voltage applied to the primary winding? So that's got to be 58%, right? We got 120 divided by 2.8 gives us 0.5769, so basically 58%. It's kind of cool how 58% is like a number that keeps coming up in a number of different areas of electricity. So we got 58% of the voltage being applied to the primary of the transformer. Considering that H1 and H2 are connected between A and neutral, calculate X1 and X2, X2 and X3, X1 and X3. So you can just do a quick diagram there. And we've got 120 on the primary. The ratio is normally 2.8 to 120. So the ratio between the windings is 1.73 to 1. So if we have 120 on the primary, then we have root 3 less on the secondary there. So it just ends up being root 3 because it's 120 divided by 2.8. So that gives us 69 volts on the secondary there. Okay, then we've got number 5. Connect up the circuit shown in figure 1-4 using transformer T1. Turn on the distribution transformer to determine the voltage between X1 and X2. Okay, so that's just connecting up line voltage. So on that diagram there, there should be H1 and H2, right? So we're going to draw line 1 to X1 to H1, and then we're going to do line 2 to H2. Okay, and then we're going to take a voltage reading from X1 to X2, X2 to X3, and then X1 to X3. So first voltage there is X1 to X2. Okay, so we have 2.8 here. The ratio is that when we have 2.8 here, we have 120 and 120, because it's a root 3 relationship between those two. So we should have 120 volts on that secondary side. Beautiful, there's 120 volts, okay? If I turn this off, well, we've already seen the 2.8, but let's just show the 2.8 quickly, right? So line voltage is 2.8 there. So you can see, you can show them like, depending on when the compressor turns on, that voltage of 2.9, 2.8 sometimes drops to 2.07, 2.06 on the floor. So you can show them that when large inductive loads are connected up on the rest of the floor, that the voltage is sometimes reduced. So that takes care of the voltage between X1 and X2, 120 volts. The next voltage between, then it says, okay, well, obviously between X2 and X3. So we should be asking him this voltage as well, right? So we should see the 120 volts on the other winding there. So that's good, okay? Then it says, turn off the distribution trainer and connect the primary windings of the transformer between A and neutral. So this line 2 is then going to neutral. Don't forget to put in this jumper here for the neutral. I mean, I guess you could just connect up to there, right? But we'll throw that jumper in there. Okay, and then we said that if it's root 3 less, if we have 120 volts here, then we're going to have 1.732 less on the secondary side. So we should have 120 volts on the primary, and then we should have 69 or 70 volts on the secondary there. Beautiful, 69. Excellent, okay? And if we look there, obviously the voltage is 120 on the primary. Okay, so 120 on the primary. Ratio still stays the same, so that's primarily what we're looking for, is the discussion of the ratio of the windings. In that if you put a lower voltage to the primary, then obviously you're going to get a lower voltage on the secondary. that takes care of page 5. Looks good. We'll stop there because the next one's on single phase paralleling on page 6 there. Okay, so on page 6 of the instructor manual, let's make sure that that's the same page here. So now we're off by 1 page. So bottom of page 5, it says single phase paralleling. When greater capacity is desired, two transformers may be connected in parallel. Single phase transformers with either additive or subtractive polarity may be paralleled successfully if the following conditions are met. Voltage, tap ratings, percent impedance, and frequency ratings are basically identical. And it says connection configuration for two bushing transformers for 120 volt 240 service is shown in Appendix B. So in the instructor manual, that is page 33. In the student manual, that is page 29. So let's hook up the parallels of the two transformers there. So single phase paralleling on page 29 of the student manual there. So for that guy, we've got, looks like A is going to H2 of both of the transformers. So let me remove these guys. So we've got the A phase going to, looks like H2 of both single phase transformers. So H2, doesn't matter where we go. Okay, so same polarity on each transformer there. Okay, then H1 is going to neutral or B. So let's do B. So we get the 2-8 to this guy. Okay, that's good. And then it says on the secondary there, we've got X1 to the B phase. Okay, so let's do that. So you got these bus bars on the bottom here. Let's move the meter over here. So it says X was X2? No, sorry, X1. They've got showing to the B phase there. Okay, and obviously the other one is going to the same point. So X1 to the B phase. Okay, then we've got X3, which is going to the A phase. Okay, the other transformer is doing the same. Okay, then we've got X2 to the neutral, and it looks like they've got the neutral grounded there. So center tap going to our neutral bus. Do that on both of these guys. Okay, and then in that diagram they do have the neutral bonded to ground. Okay, so there or here, right? Come on. Okay, and then we're looking at voltages across each of the phases there, right? So we can go, let's go between A and B first. So this one's supposed to be 208 volts into each of the primaries there, and then we should still have 240 volts on the secondary there. Gorgeous. Okay, and then we should have 120 volts between any line and neutral connection there, right? So if we go between line A and neutral, we got 120, and if we go between B and neutral, 120 volts. Beautiful. Okay, and each of these guys have 208 volts on the primary, 120 volts obviously on the secondaries there, paralleling to our bus on the bottom there. Sweet. The other thing that it's asking for is there anything else that it says there? Oh, it says neutral or B, right? So if you wanted to, I guess you could change the B to the neutral. So that would be 120 volts to each of the primaries there, and then we saw 69 volts on the secondary, right? So let's see what that is. Again, I've neglected to put that jumper in. My goodness. There we go, 69 volts from B to neutral, A to neutral. Okay, and then from A to B, we should have 138, double that voltage. Sweet, and then obviously the voltage going into the primary of each of the transformers is going to be 120 volts. Cool. And then you could also have them check between the two H2s, right? So obviously no voltage there. In between the two H1s, obviously you want to have them turn this off as you're doing that. But the H1s should also have 0 volts between them. Sweet. Excellent. So you can use this to show the paralleling of the transformers. And then you can also show them the ratios obviously stay the same between the T1 and T2 transformers there. Excellent. Okay, so on page 6 of the student manual, 7 of the instructor manual, they go through the 3-phase banking of single-phase transformers. So you can have a quick discussion on delta to delta, Y to Y, delta to Y, Y to delta, and then discuss the phase shift. Like if you have the same animal from delta to delta, there's a 0 phase shift. But if you go from one animal to another, from delta to Y, or from Y to delta, there is a 30 degrees phase shift. The next one on page 7 of the student manual, and obviously page 8 of the instructor manual, is the delta to delta 0 degrees phase shift connections. So what I'll do is I'll stop it here, and then we'll do a quick diagram going through that one that they've given, and then we'll come back and connect it up, and then take those voltage readings between A and B, B and C and A, and they should be identical to 40 volts.
Okay, so let's take a look at the delta here. So we have single windings on the primary here. First of all, this is a great program if you haven't used this yet before. It's Microsoft Whiteboard. You just download it from the App Store, you tie in with your Microsoft account, and then like the drawings you do get saved to the cloud, and you can use them on different devices. And then when you draw on an image like this, then it groups it together. So it's very cool. All I've done is just taken a screenshot of the manual, cut this out, and then I can do my drawing beside here. So first one thing is we have our primary here. So I usually show that nomenclature of A to B, B to C, and C back to A. So we got A to B, B to C, and C back to A, both in the primary and the secondary. So there we can see that the 2 8 volts from line to line is being applied to each of the windings in the primary. So we have H1 to A, which is seen right here. H1 is going to A. Then we've got H2 going to B, so H2 is going to B. H1 of T2, so H1 of T2 is going to B. Looks good. And then H2 of transformer 2 is going to C. So that is going over here, tying it to C. And then finally, the transformer 3, H1 is going to C, and H2 is going back to the A. So H1 going to C, H2 going back to the A. Beautiful. So we got A to B, B to C, and then C back to A. On the secondary side, I've drawn out the 2 windings that are on the secondary. The ratio there is 2 8 on the primary, gives us 120 volts on each of the secondary windings there. So voltage from X1 to X2 is 120, and from X2 to X3 is 120 as well. The wiring here, we can see X1 is coming down here and tying into A. So I have X1 going to A. Then I have X3 going to B. So remember, A to B, B to C, C back to A. So X3 is going down here to B. Okay, then on the second transformer, we have X1 going to B. Okay, so X1 coming over here to B, and X3 going to the C phase. Excellent. Or I guess line C instead of C phase. So X3 going to X3 going to C right here. Then on the final transformer 3, we have X1 to C, which is seen right here. And then finally, X3 is going back to A. So X3 is going back to A there. So if we have 2 8 120 on each of these guys. These guys are connected up in series, so they'll sum together to give us 240 out. So we should have 280 3-phase in and 240 3-phase out. So let's go back to the shop, take a look at the wiring, and see whether in fact we do get 240 volts output.
Alright guys, delta to delta now. So we've got the 3 transformers, and then hopefully you've gone over that little trick where you can go A to B, B to C, and then C back to A. So we have A going to H1 of T1, right? Then the next one, the other side, is going to be H2 to line 2, right? So there's that trick A to B, right? This one should be B to C and C back to A. So keeping going with that diagram there, looks like H1 and H2 are connected up together, back to line 2. Okay, then we've got, so that's B. This one's got to go back to C, right? So this H2 of transformer 2 has to go to line 3. Okay, so that's B to C. We're going to jumper that one. So that H2 and the subsequent H1 of transformer 3 together there. So A to B, B to C, C, and H2's got to go back to A now. Coming. Okay, excellent. So at that point, I would have them turn it on and make sure that everything was good for their primary there. So everything's cool for the primary there. If we take a voltage reading on the primary, so between any of these windings here, they should all be the same. But let's see what we got. So we got 2.8 on the 3rd transformer primary. 2.8 on the 2nd transformer primary. And 2.8 on the 1st transformer primary. Excellent. Okay. I would maybe get like different color leads for the if they're using these terminals going to the meter, because as I'm pulling them out, I'm like just randomly grabbing a red and a black there, right? But we want to make sure that they're not grabbing two jumpers that are not connected to the meter and then shorting out the supply there. So everything's cool there. We got 2.8 to the delta, and it's holding there. Nothing has blown. Okay, on the secondary there, it looks like we have, let's see, X1, and X1 is going to C. So what's going to A? So they've got X1 on the 1st transformer going to A. So because we fed this winding here with the A phase there, then we're going to grab the A phase off of that terminal there. So X3 is going to our A phase, yes? Is it? No, sorry, X1 is going to, donkey. X1 on this guy is going to the A phase here. Okay, what else? Got my hand in the way, sorry. Okay, so that's A, and then the other side of that guy should be B, right? So X3 is going to B. So A to B, same as we had on the first one. The next one should be B to C, right? So if we take a look, X1 of transformer 2 is going to B. So X1 transformer 2 is going to B. Next one, X3 should go to C, right? So yes, X3 is going to C. Okay, and then on the last transformer, we should be going from C to A, right? So X1 on the 3rd transformer is going to C. And finally, X3 is going back to the A phase. Excellent. Okay, we've left these terminals here available so we can take voltage readings. Interesting that they have X2 jumper to ground. Eh? That's strange. Why would you do that on a delta to delta? Okay, let's do it. Let's take a look without that ground terminal there on T1. Take a look at the voltages. So let's see whether she holds first. Okay, so it's holding. Let's look at the voltage between A1 and B1. So that is down here, right? So that's our bus on the secondary side here. So we had 2.8 going into there. These guys are seriesed up, so we should have 120, 120. So we should have 240 volts on each of the secondary windings there. Excellent. 240 volts between A and B. B and C should be the identical voltage there. Okay, 240 volts. And then C and A should be identical as well. Excellent. Okay, let's turn this off. Everything worked out there. Let's do X2 to ground. See if anything changes there. Nothing seems to be changing there, right? Same voltage that we saw before. AB. Yeah, everything's still 240 there. I'll have to look into why that X2 is actually grounded on that diagram on page 7 for the delta delta zero phase shift. Okay, turn off the says at the bottom of page 7, turn off the distribution transformer trainer, leaving this configuration connected so as to compare it with the next configuration. Okay, so we'll keep that connected and we'll check the next configuration. All right, guys, so page 8 of the student manual, page 9 of the instructor manual. It says that to repeat the circuit shown in figure 1-6, use transformers T4, T5, and T6, and lines A2, B2, and C2, connect bushing X2 of transformer 4 to the ground terminal. So we're doing identical connections there. So we can pause it here. I'll quickly do those connections and then come back to you. So at this point, we now have a parallel delta there, right? We have one delta on the left-hand side, we have one delta on the right-hand side, and it's asking us for the voltage between lines A1 and A2, B1 and B2, C1 and C2. So I've got my voltmeter right here. What I've done is, so these 2 points are tied into X2 of 1 and X2 of T4, and now they're asking us for the voltage between these 2 buses, right? So between A1 and A2 should be identical, right? So when we turn this on, so what did I do there? I got 240. Okay, so now we have the parallel delta on the right-hand side. So we have a delta to delta 0 degrees phase shift on the left-hand side with T1, T2, T3. A delta to delta 0 degrees phase shift on T4, T5, and T6. Remind them to be careful because like the secondary sides are ass backwards. They're a mirror image of the primary side, right? So you can see that on the top there, H1 is on the left-hand side, but X1 is on the right-hand side. So I made the mistake in my second set of T4, T5, and T6, assuming that this one was X1, right? But that's actually X3. So once we turn this guy on, they want us to take a look at the voltage between the 2 buses, right? So I'm going to look at the 2 A buses, right? So I'm going to look at the potential difference between these guys. And because we've got everything hooked up in parallel and this same phasing, then we should have 0 volts between those guys. And you'll notice that the X2 of both transformer 4 and transformer 1 have been grounded there. Okay, so when we turn this on, you can see that there's no difference in voltage between those 2 buses. If I drop her down to B1 and B2, then there should be no difference in those 2 buses. Excellent. And if we look at the 3rd bus, then everything should be the same there. Beautiful. So that's good. That takes care of 7, right? Considering that the two transformer banks are identical, the voltage between the corresponding lines of the transformer bank is approximately 0 volts. One can assume there is no phase shift between the corresponding lines of each transformer bank. Okay, turn off the distribution transformer, leave the configuration connected to T1, T2, T3, so as to compare it with the next configuration. Disconnect the delta-delta configuration 0 phase shift on T4, T5, and T6. So now what you're going to do on page 8 of the student manual, step 8, is that you're going to do a delta-to-delta 0 phase shift on this side, and then on this side we're going to do a delta-to-delta 180 degrees phase shift. Before we do that, we can quickly check the voltages. Do I still have this on? We can check the voltages between the bus here, right? So between A and B on our secondary of the second transformer, we have 240. Between B and C, we should have 240 as well. Beautiful. And between C and A, we should have 240 as well. Okay, just double checking on the other transformer here. It's messy, eh? There's like, we may not be able to use those shrouded leads because look at how many leads you actually need just to get this one configuration done. So this is A and B on the first bank of transformers, so 240 there. B to C should be 240. Okay, and then C back to A should be 240 as well. Beautiful. So that makes sense. So we have 240 between any of the lines on this bus on the secondary side, or this bus on the secondary side of our second bank of transformers, and then the A phase on either one, 0 volts difference, B phase, 0 volts difference, C phase, 0 volts difference. So now turning it off, we're going to remove all of these terminals here. Oh, no. Not the primary. The primary is staying the same, right? It's the secondary that's changing here, right? So this is what I mean. You got to make sure that they've turned off the power because you're quickly removing leads. So shrouded leads would be the best for these guys. So let me pause it here, and I will reconnect with the 180 degrees phase shift on the secondary side here. Okay, so on page 9, you can see the 180 degree phase shift diagram. That's figure 1-7. So you'll see there that X3 goes to A and X1 goes to B, right? So it's 180 degrees phase shift from the previous diagram there. You'll also notice that, again, the X2s are tied to ground there. So what they're asking for is, it says back on page 8 there, connect the circuit shown in figure 1-7. Use transformers T4, T5, and T6 and lines A2, B2, C2. Connect pushing X2 of transformer 4 to the ground terminal, which we've done. Turn on the distribution transformer trainer and determine the voltage between A2 and B2. So between these two bus here, so we got to go between A2 and B2. So you may want to have the students keep these lines open, because then you can leave your meter in the center there and just quickly check those guys. So before we saw 0 degrees phase shift, 0 volts between those. They were the same potential difference. And now we got 240 volts between those guys. Okay, let's take a look at the next one. So obviously that's 240, so this one must be 240 volts as well. So because they are out of phase, then we're getting 240 volts there as well. And between the two C phases, we're getting 240 volts. Ooh, no, we're getting 415 there. What did I do wrong there? What am I between the two C phases there? What the heck did I do wrong? Let me check it. So I didn't do anything wrong. That 415 volts is just the fact that I wasn't reading the measurements I was supposed to be making. So it's actually asked for us to look at the voltage between A2 and B2. So on the secondary side, this should be 240 volts. Okay, that's good. Okay, then it asks us between B2 and C2. So that should also be 240 volts. Okay, and then finally C2 and A2. That should also be 240 volts. Beautiful. Okay, Then it says below, determine the voltage between lines A1 and A2. Okay, so now we're going to look at A1 and A2, so the two opposing bus here. I would think that would be 240 like we saw before. Okay, so there's 240 volts there. Okay, then between B1 and B2, yeah, okay, that's going to be 240 volts as well. Okay, then it says use two lamps in series to carry out the voltage measurement between lines C1 and C2. Okay, so we need to remove these guys. Okay, and we need some other jumpers. Okay, so between C1 and C2, use two lamps in series. Okay, so C1 has got to go to one lamp, and then this guy, the other side, is going to go to C2, and then we need a parallel jumper. I have one extra lead here. Okay. Man, there's a lot of leads that are needed for these guys. So those guys are in series, and then we're going to look across the load here. Okay, so let's turn this guy on. It says in the answer book it says 425 for the voltage. So I'm getting 377 across the two loads there. Okay, let's remove the two loads there. So I'm going to remove those two loads there. And I'm going to look at the voltage between those 2 points. So I'm removing those two jumpers there, connecting up between C1 and C2, and let's just look at the voltage without a load connected up there. So this is supposed to be 425, and I'm getting 414 as the voltage between C1 and C2. So there's obviously some internal resistance on these transformers that when they hook up these loads there, then it's reducing the voltage that's stated in the instructor manual. So we're going to have to let's take a look at the diagram and see why that voltage is so high on the C phase there. What's interesting is that these voltages are apparent when this X2 is grounded on either one of the transformers. If I remove that X2 connection there, then you'll see that the voltage between each of the lines now looks like 215 between these two C phases. On the B, I got 224. So these are now floating voltages, no reference to each other. And they're fairly similar to each other. There's 216, right? So again, 216 on the A. $225 on the B, and $215 on the C. That's without either one of the transformers being grounded, or without them having a reference between them, right? So if we bring these guys, the X2s of the first transformer, and ground them, then they both have a reference that is tied together. So at that point, now I've got the 416 on the C phase, and my B and A go to 240. 240 there, and 240 on this guy. Cool. So I will not lie. That's something that I have no explanation for at the moment, but hopefully I'll follow up with the diagram on why the A and B are 240 volts, and why the C phase is 416, and why that reference between the two for the X2 of transformer 1 and transformer 4 are both bonded is crucial in order to have those voltages actually become apparent.
Okay, this was my best explanation as to why we were seeing 416 between the two C phases being C1 and C2. So keep in mind that the two transformers are connected to ground on either T1 or T4, right? So that creates a common connection between the two circuits there. So all I did was I did this as a kind of like a buck boost. So I went from here, from the voltmeter, I went through the winding. So I'm picking up 240 here on T2. I'm picking up 120 on T1. Then I'm going from this ground connection. That comes over to this ground connection. I'm picking up 120, negative 120 here, negative 240 here, and then back to the voltmeter here. The math here was just the vector sum of these guys. So here I had 240 volts and 120, but this 120 is happening at 0 degrees. This 240 volts is happening at 120 degrees. So I just did the vector sum between these guys. So x component being cos of 0 degrees times 120 gives me 120. Sine of 0 degrees times 120 gives me 0, obviously. Then for the x component of the 240 at 120, this should say 240 at 120. Okay, that x component is the cos of 120 times 240 gives me negative 120. And then the sine of 120 times 240 gives me positive 28. These guys cancel out, so I've got 0. This gives me 28, so it gives me positive 28 as the net voltage between these guys, or the vector sum between these guys. On this side, I have 120 volts and 180 degrees, because this one was 180 degrees phase shift. So this 0 degrees has moved over 180, and this 240 has moved from 120 over to 300. This is incorrect as well. This should say 300. Okay, so 120 at 180 degrees gives me an x component of negative 120. 240 at 300 degrees, so cos of 300 times 240 gives me positive 120. Sine of 300 degrees times 240 gives me negative 28. Again, these cancel out, and I'm left with negative 28. Now I just have the sum of 28 volts on this side minus the negative 28 that I see on this side, summing to give me 416 volts between those two, C1 and C2. I would love for some help with this to tell me whether I'm completely wrong or whether this is the correct way to figure out the 416 volts between the two C1 and C2 phases there. One being from a 0 degrees phase shift, the other from a 180 degree phase shift. The voltages that we found from B1 to B2 were 240. So following the same thought process, I just went from, the voltmeter over here. This has a connection up to this point right here. Then following through, we would pick up 120 volts. Then it goes to the ground connection of the T1. And then from that ground connection on T1, it's coming over here, picking up another 120, but this is obviously 120 in the opposite direction. And then coming back to the source here. So we had 120 volts minus the negative 120, giving us 240 volts between B1 and B2. So only going through one winding on T1 and one winding on T4, summing to give us 240. The one for the C phase, the A phase, we have voltage coming through here. That comes up to this point right here. Again, goes through one winding on T1 to the common ground connection. Then from that common ground connection through in the same direction through the other 120 volt winding on T4. And again, 120 volts minus the negative 120, summing to give us 240 volts between A and A, B and B. And then we've already gone through the voltage between the two C phases. So we had 240 between A and A, 240 between B and B, and 416 between C1 and C2. Okay, next one is on page 10 of the student manual. So next one we're doing is an open delta 0 degrees phase shift. So you can go over with your students the open delta and the fact that you can get 3 phase out of only 2 transformers. So again, we have on these guys, we're going from, looks like from A to B, right? So we have two 8 volts on each of the primaries here. That mnemonic, remember, we have A to B, right? So A to B, and then B to C, and we're just missing the C to A portion of the circuit, right? So we have A to B, B to C. We're missing the C to A portion of the open delta. Okay, we have H1 going to line A, so X1 is going to go to A as well if we're going to have this 0 degrees phase shift here. So you'll see on the secondary side that, remember, we have 120 volts on each of these guys. Because of the ratio, right, we have a 1.732 to 1 ratio. So the ratio of the transformer doesn't change whatsoever. So our secondary voltages remain at 120 volts. We're going, again, I mentioned the fact that A was being fed from A here, or sorry, H1 is being fed from A. So X1 is feeding A here. So this should be A to B, right? And then this guy should be B to C, right? So A down here, X3 is going to B, okay? And then we can see here that X1 is going to B, and finally X3 is going to C. Okay, so we should be able to get 3 phase out even though we have 2 transformers here. What would obviously be missing would be VA, right? There's a loss of VA because we have an additional whole transformer that's missing on this transformer. So same voltages, but not at the same power output. So these guys are both summing together. So we should get 240 volts between these guys. We should get 240 volts between these guys. And we should see 240 volts between A and C. Okay, so our voltages below should be 240, 240, and 240. Do your results demonstrate that it's possible to supply a 3-phase load with only 2 transformers? We should be able to see that, in that we'll see the 3 voltages, but we don't have a scope or anything. It's not like we can actually see the sine waves. All right, let's go back to the shop and see how this is connected, and see whether we do in fact get 3 voltages from A to B, B to C, and C back to A.
All right, guys. Next one is the open delta with 0 degrees phase shift. In the student manual, that's page 10. In the instructor's manual, that is page 12. So it looks like we've got A phase feeding H1 of transformer 1. So H1 is going to be fed from the A phase. Okay. Then the next side is going to go to the B. So A to B. Right. So B phase is now feeding H2. Okay. And then we got should be B to C now, right? So H1 should be fed by B. That's good. So transformer 2, A to B, B to C. So this guy goes to B phase, C, then feeds H2. Looks good. And then that's it, right? So we've got an open delta here where we've got A to B, B to C. Okay, that's our primary there. Let's juice that up. Nothing's popping at the moment. Everything's good. Okay, let's take a look at the secondary now. So we got X1 to A. So again, this one's a 0 degrees phase shift. So that means that if we're feeding H1 with the A phase, then X1 is then going to feed our A phase as an output. Okay, because remember that H1 and X1 are going to have the same relative polarity. And then X3 is going to go to B. So again, we got A to B. This guy is going to feed B phase. Okay, so A to B, and then it should be B to C. So remember that these guys are backwards. So now X1 is going to go to B. So X1 of this second transformer is going to feed B. Okay, and then we got X3 that's going to feed C. So X3 of this guy is then going to feed the C phase. Good. Okay, let's turn on. Breaker's holding. Okay, and now we're going to look at the voltages between, determine the distribution transformer, and determine the voltage between A and B, B and C, and C and A. Okay, so let's take a look. So again, we're looking at the secondary, well, let's look at the primary voltages first if we want. Just make sure there's no glare on that screen there. Okay, that's not bad. Okay, so primary voltages should be 208. Okay, so we're on AC voltage. We got 208, 210. Okay, beautiful. So that's one winding. Second winding here should have 208 applied to it as well. Beautiful. Okay, and then our secondary windings are each 120. Let's take a look at the voltage between the A and the B phase. A1 and B1. Come on, babe. Okay. Okay, so we got 240 there. So we have the same as we had before with the closed delta in that x1 and x2 gives us 120, x2 to x3 gives us 120. The sum of those guys are giving us 240 volts out. Okay, between B and C should be an identical 240. Yes. And then between C and A, we should have 240 volts as well. Very nice. Okay, so the open delta is awesome in that you can use two single-phase transformers to create a three-phase bank. Like we clearly have three separate voltages that are outputting from two transformers. Okay, then the next one says open delta 0 degrees phase shift versus open delta 0 degrees phase shift. Okay, so repeat the circuit shown in 1-8 using transformers T4, T5, lines A2, B2, and C2. Connect bushings X2 to the ground terminal. Okay, so let's do this identical wiring on the other side here. Okay, so this is where we're gonna compare the two open deltas, right? So we're going to feed the primary. So the primary is going A to H1. Okay. B to H2. Okay, then on the second transformer we have H1 being fed by B. B phase feeds H1, and then the H2 goes to the C phase. Okay, looks good. Then on the secondary side there we have X1 feeding A. So X1 feeding A. Then we have X3 feeding B, so A to B, and then this guy should be B to C, so X1 of transformer 2 goes to B. Okay, looks good. And then, wait a minute, X1 of transformer 2, okay, and X3 goes to C. Excellent. Okay, so now we've paralleled the two open deltas, and we're going to look at the voltage between A1 and A2. So we're going to look at the voltage between those 2 points. Let's pull this bad boy out of that circuit there. Let's put it back here. Okay. Let's make sure that I haven't messed anything up. Okay, the breaker's holding. So I'm now going to test out the voltage between A1 and A2. So those 2 bus, those guys are both 0 degrees phase shift. So there should be virtually no voltage difference between those guys. So we got 7 volts difference between them, right? You guys see that? The wires are in the way there. Okay, so we got virtually no voltage difference between those 2. Okay, like 6 volts difference, right? Remember, it's a floating voltage. Okay, let's take a look at the voltage between the B phases now. Okay, so secondary side on the B phase, we got, again, basically 5 volts output there. Okay, so virtually no difference between those guys. And on the C, they should be in phase as well. There we go, 7.62 volts difference between them. So virtually no difference between those 2 phases. So what can you conclude about the phase shift between lines A1 and A2? There is virtually no phase shift between them. Okay. Then it says turn off the distribution transformer trainer. Leave the open delta configuration connected to transformer and transformer 1 and transformer 2, so it's compared with the next configuration. Disconnect the open delta 0 degrees phase shift on T4 and T5. So now we're going to probably do this guy at 180 degrees. So let me pause here and then we'll connect those guys and we'll be back to you. Okay, before I do that, I neglected to notice that I was supposed to ground X2. So we have those floating voltages, right? So X2 is supposed to be grounded for transformer 1. And transformer 4 is supposed to be grounded on X2 as well. Let's see if that eliminates that floating voltage of like 5 or 6 volts there. Let's see if there's a glare on the image there. Nope, looks good. Okay, so let's see. We're now testing between the two C phases. There we go. So no voltage difference between those guys. Now that we have bonded the X2s together, transformer 1 and transformer 4. Okay. Then next one, 0.053 volts AC, so no difference there. And on the A, no difference between those guys as well. Okay, so in order to see that that zero voltage difference between the A, B, and C phases, it's crucial to have the X2 bonded to ground. Okay, now let's do the 180 degree phase shift on the second bank of transformers there. All right, guys, so in the student manual, we're on page 12. In the instructor manual, we're on page, looks like 14 now. So we're now on the 180 degrees phase shift. So we're going to feed H1, so I've kept the H2 tied to ground there, so don't forget. The A phase is feeding H1, so A is feeding H1. B phase is feeding H2, so it looks like the primary is staying identical. Okay. H1 is feeding from B, so A to B, B to C. So this guy is going to be fed from B phase. And then, let's see, H2 is fed from C, yes? Yes. Okay, H2 is fed from C. Okay, now on the secondary side, we're going to do the 180. So X1 is going to tie into B. So X1 is going to feed the B phase. Okay, and X3 is going to feed A. Okay. And then on the second one, we got X1 feeding C. Looks good. And X3 is going to feed B. Okay, let's turn this on and make sure that we haven't messed anything up. Looks good. And what are we taking? We're looking at A2 and B2. We're looking at our secondary voltages between A2, B2, B2, C2, and C2 and A2. Okay, so on the secondary side, on between the phases, so between A and B, should have 240. Okay, looks good. We got 240 volts there. Okay, let's take a look at the B and the C. Okay, so B and C should be also 240. Looks good, 242. And between C and A, we should see 240 volts as well. Very nice. Okay, so even though we have them 180 degrees out of phase compared to the first transformer, the secondary voltages are still at 240. Okay, so now we're going to look at the voltages between the two transformers. So this should be interesting in that we looked at the delta to delta being 0 degrees and 180 degrees out of phase. And now we're looking at an open delta, and we'll see whether we have those same voltages. So now we're going to look at these two bus, right? So we're going to look at A1 and A2. And that voltage is 240 volts. Okay? Between the two B phases, so identical to what we had with the closed delta, where we had 0 and 180 degrees, also 240 volts. Okay? And now let's see what we have between the C phases. be interesting because this is an open delta, it's not a closed delta, right? So let's see what that voltage is between the two C phases. Okay, so now we got the same voltage, we got 418 volts on the 417 volts between the two C phases. So identical voltages to what we saw on the closed delta. So again, we have a 0 degrees phase shift here on the secondary. We have a 180 degree phase shift on the secondary of the second open delta. We had 240 between the two A phases, 240 between the two B phases, and now 416 volts between the two C phases. Identical to what we saw on the closed delta phase shift, voltage differences between the phases.
All right, guys, next one is the Y to delta. We've got the 30-degree phase shift now because we're going from one configuration to another. So Y to delta 30-degree phase shift. That means that our primary is being connected up as a Y. So you can see here that all of the H2s are tied together here. That means that we're going to have 208 volts between any of our lines up here. Right, so 208 between these guys, 208 between these guys, and obviously 208 between the A and the C. Those guys are now feeding each of our transformers, but H2 is tied together there. That means that we're going to have √3 less voltage, so we're going to have 120 volts on each of these primary windings. Okay, the ratio here is still 1.732 to 1 from our primary to our secondary. That means that we're going to have 69 volts on each of these guys. And because we have a delta, then the delta is going to provide the sum of those two voltages. So we should see between A and B, we should see 138. Between B and C, we should see 138. And then between C and A, we should see 138 volts as well. If we wanted to draw that out, then we could go like this. We could just quickly show our connections here. Right, so we have H1, H2, H1, H2, H1, H2, right? So all of our H2s are tied together there. A is going to feed H1, B is going to feed H1 of our second transformer, and then C is going to feed the third winding there, all tied together at H2, right? So that would mean we have 2 8-volts on each of these guys. Okay, looks good. So let's see if that's correct. A feeding H1, yes. B feeding the second transformer, and C feeding the third transformer. Excellent. Okay, so these guys are T1, T2, and T3. Okay. Iron core, and then we've got the secondary there. Secondary is a delta. So we have a center top there. So 2 windings on each of our secondary windings here. Okay, so then we'll start off here with X1, X2, and X3 for transformer number 1. Okay, let me just get rid of that because we're actually going to put a ground on the X2 of that guy. Right, so that guy is right here. Okay, so this is transformer 1. Then we go X1, X2, X3 for transformer number 2, and X1, X2, and X3 for transformer number 3. Okay, transformer number 1, we have X1 feeding the A phase. Okay, so this is going to feed our A phase here. Okay, X3 is being tied into B, right? So there's A to B. Okay, we can see that X1 of transformer 2 also ties into B, and X3 of transformer 2 is going to go to C. Okay, so this guy is going to feed C. Okay, and then finally for transformer number 3, we have X1 of transformer number 3 feeding the C phase. Okay, and then finally X3 of transformer number 3 should be tying back into the A. Okay, so X3 is tying back into the A. Each of these guys, so I screwed up here. We have 120 volts on each of these guys. right? So we have 2.8 as the source, 120 volts on each of these guys, leaving us with 69 volts on each of these guys, and our output is going to be 138 volts, three-phase. We're going to have, in this one, we're going to have 2.8 in, 138 volts out. Okay, let's take a look at this one in the shop and see how we connect this up and see whether we do get 138 volts out.
Okay, next one, guys, is the Y to delta. We're on page 13 of the student manual, page 16 of the instructor manual. So anytime you have a delta to Y or Y to delta, there's going to be a 30 degrees phase shift between those guys. Let's start off with the Y connection. So I got phase A going to H1. I always say phase A. It's line A to H1. But for some reason, I've always said phase. We got phase B to H1 of the second transformer. Okay, then we've got the third transformer, H1, being fed from the C phase. All of our H2s are going to be tied together now. So we're going to create that star connection between the H2s. Okay, so those guys are all tied together there. And do we have to ground that? No, it looks like it's floating at the moment, right? We're going to ground the X2 of the secondary there. So we're going to do now a delta on the secondary side now. Okay, so we got X1 going to A. So again, we fed H1 from A. So now we're doing X1 to the A phase here. And then we've got X3. Well, you know what, let me do that in a different color. So on the secondary side, let's use our blacks here. So I got X1 to A. Okay, then I got X3 to B. Okay, so A to B. Okay, then X1 should be feeding A here. So, no, sorry, should be feeding B, right? So X1 goes to B, so A to B, and then so A to B, B to C. So X1 is feeding B, X3 is feeding C, yeah, okay. Looks good, and then we should go C to A, right? So X1 of the third one goes to C, looks good. So this guy feeds C. And X3 is now going to complete that delta and go back to A. Good. Okay, let's turn this on. Everything's good, everything's holding. Okay, and now we're going to look at the voltages. Turn the distribution transformer, turn the voltage between terminals H1 and H2 of the transformer. Okay, so we're going to look at H1 and H2. What I neglected to do again is I neglected to, they want me to bond X2 to ground here. Let's do that. Okay, and the beginning thing we're looking at is the voltages on the primary side. Okay, so between H1 and H2. Okay, so we have a Y connection now, so we have √3 of our line voltage here. So line voltage was 2.8. We now have 120 volts on each of the primary windings. You can see here that on our second primary winding, we should have 120 as well. Okay, looks good. And then on our third transformer, we should have 120 volts. Looks good. Okay, so the ratio remains the same between the primary and the secondary. So determine the voltages between lines A1 and B1, B1 and C1, C1 and A1. Okay, so we're going to take this guy off. We're going to look at the voltage between A1 and B1. So we got 138 volts between those guys. Okay, and we should have equal voltages between everything. So between B and C, we should also see 138 volts. Okay, which we do. And between C and A, we should see 138 volts as well. Excellent.
Okay, so next one we're doing is the Y to delta 30 degree phase shift versus the Y to delta 210 phase shift. So first thing we need to do is set up T4, T5, and T6 in a Y to delta configuration. So same as we did before on the primary here. So looking here, we have A to H1, we have B to H1 of transformer 5, and then C to H1 of transformer 6. All of the H2s are tied together and they're not grounded. They're just floating there as that center tap. So that means that, again, we have 208 volts as our line voltage, and then we'd have 120 volts as our phase voltage. Okay, so 120 volts phase right across. And we've already seen numerous times that the line voltage between A and B, between B and C, and between C and A is 208 volts line voltage. Okay, that 120 volts coming in is going to give us 69 volts on each of these guys. Okay, they're tied together with the X2, so we should see a 138 on A to B, 138 from B to C, and again 138 from A to C. So identical to the previous Y to delta transformer. So the voltages on the secondary will be identical, but they would have been phase shifted to 210 degrees. And then after this, we're going to look at the voltages between the bus, between this transformer and the previous transformer.
Okay guys, next one. We're on page 15 of the student manual and we're on page 18 of the instructor manual. So it says we want to do a Y to delta 30 degrees phase shift versus a Y to delta 210 degrees phase shift. Okay, so let's do the primary for the second bank of transformers there. So it looks like all the H2s are going to tie together again. So primaries are identical in that the H2s are tied together. Okay, now we're going to feed the primaries from H1 of the first transformer is going to the A. So identical to the first guy. This is going to feed our H1 of the second transformer. And this guy is going to feed the H1 of the third transformer. Okay, so primaries are done there for the Y. Okay, then we need to do the delta on the secondary side there. But these guys are going to be at 210 degrees phase shift now. So we're going to have, let's remind ourselves to do X2 to ground. We have to have a common reference point between the two transformers. Okay, so that's X2 to ground there. Okay, and now we're going to have X1 feeding the B phase. So X1 of our first transformer is now feeding the B phase. X3 is feeding the A phase. So X3 feeding A. Okay, second transformer we have X1 feeding the C phase. So X1 feeding the C phase. X3 is going to B phase. Okay, and then on our third transformer, X1 is going to A. Okay, and we've got X3 going to C. Okay. Excellent. Let's make sure that everything holds first. Looks good. Okay, and now what are we testing out between these guys? Turn on the distribution transformer and determine the voltage between lines A1 and A2, B1 and B2, C1 and C2. Okay, let's take a look. So A1, A2, so we're now comparing the two adjacent bus bars. This one's at a 30 degrees phase shift, this one's at a 210 degrees phase shift. Okay, so the voltage between those two lines is 138 volts. Between B1 and B2, we've got an identical voltage of 138 volts. And between C1 and C2, this will be interesting to see whether we have a higher voltage here. C1 and C2, we got 240 volts between those guys. So basically, 138, 140 between A1 and A2, 140 between B1 and B2, and now between C1 and C2, we're seeing 240 volts.
Okay, so I'm really interested to see whether this works on this connection as well. In that, let's do the C phase first, right? So we're looking at the voltage between these 2 points, right? So we're looking at the voltage between here and here. Okay, we've got our common connection here at the ground and another common connection here at this ground, right? So that's where the 2 transformers are actually tied together. We've got 69 volts here. We got 69 volts here. And let's start off with this connection. So we move from left to right, right? So let's do that again. So we're going to go over here. That seems to come up to this connection right here. And then that goes to this connection. So it looks like we're picking up 69 volts and 69 volts. We're picking up 138 there. Okay, then it looks like X1 comes over here. We're trying to make our way back to this common connection here, right? So then X1 of transformer 2 goes to X1 of transformer number 1. So it looks like we've got 138 and we've got 69 volts. Okay, so we've got 69 volts at 30 degrees, right? Okay, and then we've got 138 volts at, that would be another 120, right? So that would be 150 degrees. Okay, so I just went with the 30 degrees for A, and then 120 degrees more, so 150 there. Okay, I've got my X and my Y component here. Hopefully we have enough space to figure this out. Okay, so if we're looking at the first one, we're looking at the X component. So we would have 30 degrees. We're doing the cos of 30 degrees, which is 86%, times 69 volts. That gives us 59.7. Okay, 59.75 actually. Okay, then we've got the Y component. So that would be the sine of 30 degrees, which is 0.5 times 69. It gives us 34.5. Okay, if we were to draw that out, then the X component is at 30 degrees, right? So it has both a positive and a positive X and a positive Y. Okay, then we've got the 138, that is at 150, right? So 180 here, so we had 150 over here. Okay, so that would be our 138. So looking for the X component, that would be the cos of 150. That's negative 0.86, that looks good, times 138. Gives us negative 119.5, so basically negative 120. And then should have a positive Y, right? So we have the sine of 150 times 138 gives us positive 69. Okay, so we got 59.75 positive, right? Minus 119.5 gives us 59.75 negative. Okay, and then we've got 34.5 positive plus 69. That gives us 103.5. That's positive. And then the vector sum of those guys would be 59.75 squared plus 103.5 squared. Then we'll take the square root of those guys. So we got 59.75 squared plus 103.5 squared. And we'll take the square root. Gives us 119.5. Okay, so the sum of those guys between transformer 2 and transformer 1 is going to give us 119.5 volts. Okay, so we've got 119.5 volts. Okay, and then we're going to subtract whatever this voltage is. So over on this side, following through on that diagram, a little bit messy, but we get to this common connection, right? And then we have to make it back to the C phase, right? So let's reverse engineer this, just so we don't screw this up. This is going to come to here, right? And then it looks like, let's see, that's going to come up to this point right here. Somehow we have to get to either the A or the B phase, right? So it would then come, like current would then come through the first transformer number 4, right? Okay, come over here, tie into X1. Current would go across these two, pick up 138, and then come back to the voltmeter there. So again, we have 69 and 138 there again. Okay, let's look at what angles we would be at there. Okay, so the first one, I don't know if I have enough room here. So the first guy, we have 69 volts. Okay, and that is going to be at 210 degrees. Okay, then we have an additional 138 volts, right? Because these guys are going to sum together. So we have 138 volts. And what angle is that at? That would be at 210 plus 120, right? 210 plus 120 gives us 330. Okay, and then we need our X and our Y components for those guys. Okay, so we've got 210. We're going to do the cos of that times 69 gives us negative 59.75. Okay, can we draw that out here? So our first vector there is at 210, right? So that's going to be over here. So that's definitely going to be a negative X, so that's good. Okay, it should be a negative Y as well. So we have 210, we're doing the sine of that. That's negative 0.5 times 69. Gives us minus 34.5. Okay, so identical values that we saw over here. Okay, and then we've got 330, right? So we got 270, the other vector is going to be over here, around 330. So we've got 330, we're doing the cos of that. So obviously a positive X value there. So 0.866 times 138 gives us positive 119.51. And then we've got 330, and we're doing the Y components. We're doing sine of that times 138. Okay, so that gives us negative 69. Excellent. Okay, so now we've got 59.75, but negative, right? Plus the 119.51. That gives us 59.76 positive. Okay, and then for a Y component, we have negative 34.5 plus negative 69 gives us negative 103.5. Okay, and we just found those values over here, right? 59.75, 103.5. So these guys are also going to sum with Pythagorean's theorem to give us 119.5 volts. Okay, so we've got 119 minus a negative 119.5 volts. Come on. All right, so essentially we were adding those guys. So we have 119.5 plus 119.5 to give us 239 volts. So we should have 240 on the C phase there. Okay, so that seems like it's working out, right? Because that's what we saw between C1 and C2, 240 volts. Okay, let's check out B1 and B2 and see if we get 138 now. Okay, so we'll move over to these guys. Okay, let's get rid of this. Okay, let's take a look at B1 and B2 and see if we get 138 now. Okay, so we've got our voltmeter. We're going to put our voltmeter between here and here. Okay. And we've got, let's just reverse engineer this. So we're going to go here up to this point, right? And we're going to the point where we actually get to this common ground connection. Okay, so it looks like that's coming over here, and it's picking up 69 volts off of this transformer number 1 before it goes to the common ground connection. Okay, then from that common ground connection, then it's coming up, right? And we've got to get back to the B, so we're now going across this portion of transformer number 4, okay, over to B, okay, and then going back to that point. Okay, so that looks like it works out in that we have 69 volts minus a negative 69 volts, right? So adding the 2 gives us 138 volts between B1 and B2. Nice. Okay, let's see if that works out between A1 and A2. So that voltmeter would be here. Okay, we're going between these 2 points right here. Okay, we're going to come to this point. We're trying to get to the quickest point to this common ground connection. So that easy now, that looks like garbage, hang on. Okay, so we're going to come along this first bus here, come up here, right? We're picking up the 69 volts before we get to that common ground connection. Okay, from that common ground connection, we're trying to get back to A, so we're coming up here, right, across this winding, coming back down to the A phase. And again, it looks like we have 69 volts over here, minus another negative 69 volts over here. So that gives us 138 volts from A1 to A2, 138 volts between, I may have misspoke there. A1 to A2 is 138, B1 to B2 is 138, and then C1 to C2 was 240 volts. That matches with the values that we saw on our answer sheet here. Excellent. Okay, everything seems to be working out. Let's move on to the next one, guys.
Okay guys, next one we're doing is page 16 of the student manual. It says connect the circuit shown in figure 1.2, which is found on page 17, using transformers T1, T2, and T3 in lines A1, B1, and C1. So this is page 16 of the student manual and page 19 of the instructor manual. So going off of the diagram 1.12 on page 17 of the student manual, we're going to go A to H1. Okay, next one we're going to do H2s. Looks like they're all tied together. So H2s are common between everything. Okay, and let's see, we are feeding, so we have a Y, so H1 is going to feed from each phase. So H1 from A, H1 from B, H1 from C. Okay, so that does our Y on the primary there. Then we have the delta, so we've got X1 to A, so X1 of the first transformer is going to A, X3 is going to B, X3 is going to B, yep. Okay, so X3 is going to B. Okay, then X1 of the second transformer is going to B. Okay, X3 is going to C. So A to B, B to C, and then C back to A, right? So X1 should go to C. Yep. And then X3 should go back to A. Is it? Yes. Okay. And now, this is identical to what we were doing before, but we are bonding part of this. So the X2 is now going to the neutral. Okay, and then the neutral is being bonded to ground. Okay, so X2 of the first transformer here is going to the neutral. So it's going to feed our neutral bus. And then our neutral bus is then going to be bonded to ground. Okay, let's see if she holds. Okay, looks good. Okay, so we've connected those guys up. Now we're going to look at the voltages between A1 and B1, B1, C1, C1 and A1. Okay, so let's do that first. So we're doing the voltages between these secondary lines here. Okay, so A1 and B1. You guys see that? Yep. So that one's 138 volts. Okay, it should have identical between B and C. 138 volts, and between C and A we should have an identical voltage. Yeah, 138, 139 volts. Okay, so now let's look at the voltage between A and neutral. So A on the secondary and neutral should be 70 volts. Beautiful, we got 69.3, basically 70 volts. Okay, between B and neutral, we should have 70 volts, which we do, 69.2. Okay, and let's take a look at C and neutral and see whether it's the same or whether it's higher. C and neutral is 120 volts. So we had 140 between A and B, B and C, C and A. Between A and neutral we had 70 volts. B and neutral we had 70 volts. And between C and neutral now we had 120 volts.
Okay, let's see if we can figure out where that voltage was coming from, right? Because we were looking at our values here. So we had 138, that was obvious, between A and B, B and C, C and A. Then between A and neutral we had 69, B and neutral we had 69, and C and neutral we had 120. See if we can figure out why C to neutral was 120. So let's go back to this diagram right here. Okay, so between A and neutral, we had 69. Okay, so that if we follow that through, right? So between A and neutral, it looks like we have 69 volts, right? So it's picking up the 69 volts between X1 and X2 on transformer number 1. Okay, so that seems clear there. Okay, let's go between B and neutral now. So between B and neutral, so B bus coming up here, and we got to get to the neutral there, so we'll take the shortest path. Looks like we're coming over here, going through this winding between X2 and X3 on transformer 1, number 1, and getting to that neutral there. So that's where we're picking up the 69 volts as well. Okay, it looks good. So A and B are obviously 69 volts because we're only going through one of the windings there, going from either A or B to this neutral bus now. Okay, let's see if we can find out what's happening with C to neutral and why that is a higher voltage. So we've got C, that's coming up here, and then we need like basically the quickest path to that neutral, right? So let's back engineer this. So this is going to go to here, to this point right here. Looks like, no, I don't know, it's hard to see. Maybe if we went this way through one of these windings, so it looks like we'd go through both of these guys, pick up 138 volts. Then we come over here, pick up 69 volts before going back to the ground there. So it looks like one of the paths from C to that neutral would be like this, right? Picking up the 138 between these guys, and then picking up 69 volts from the first transformer there. So with this one, we have the 69 volts, which is on transformer 1. So 69 volts at 0 degrees. And then we've got 138 volts. Let's just say that's at 120 degrees there. So the difference between these two secondary windings, right? This being at 0 degrees, this being at 120 degrees. Again, I may have the angle incorrect, but it's still going to be the same relationship here. So 69 volts at 0 degrees is going to be everything on the x-axis and nothing on the y-axis. And then 138 at 120. So first thing we need is the cos of 120, which is negative 0.5 times 138 gives us minus 69. Okay, and then the y component would be the sine of 120, which is 0.866 times 138 gives us 119.51. So there's our answer there, guys. So when we do the net voltage between these guys, 69 minus 69 is 0, right? This is basically 0 plus 119.51. So the net voltage between these two and this winding here is basically 120 volts from the C to the neutral there. Excellent. So it seems like doing this sort of, I mean, I don't know if this is correct, but finding these voltages by basically going through and doing almost like a buck boost connection there, we seem to be coming up with the appropriate values all the time. So A to neutral was 69, B to neutral was 69, and now C to neutral is now the vector sum of these 138 and 69, giving us 120 volts from C to neutral.
Okay, next one, guys. We're now going to compare this one here that we did earlier. We're on to page 18, y delta 30 degrees phase shift versus y delta 210 degrees phase shift. So page 18 of the student manual and page 21 of the instructor manual. So we're going to do the same primary. We're going to do a y primary there. It looks like H2s are all tied together there. So H2s are together. And then each transformer is going to be fed from a separate line. So H1 from A. Yes. H2 from H1 at the second transformer from B. And H1 at the third transformer from C. Okay, so that's our primary there. Secondary is going to be X1 to B. Okay, so this is a 180 degrees from the other one, right? So X1 to B. So X1 to B. X3 is going to A. Okay, and then what we'll do is we'll drop in, it also wants us to have X2 bonded to ground on the first transformer. Good, let's get these guys out of the way. Okay, and on our second transformer we have X1 of transformer 2 going to C. Okay, X3 of our second transformer is going to B. Okay, and third transformer, we have X1 going to A. And we have X3 going to C. That's okay, so on the bottom of that page it says turn the distribution transformer and turn the voltage between A2 and B2, B2 and C2, C2 and A2, and then A2 and neutral, B2 and neutral, C2 and neutral. So let's do that. Let's get this guy up and running. Where is this connected up to right now? This is connected up to my previous transformer. So let's take a look between the two output phases of this second transformer here. Okay, so from A2 to B2 we've got basically 140 volts or 138 volts. Okay, we should have identical voltages all the way through here. Okay, so let's look at the voltage between, let's turn it off. Let's look at B2 to C2. We should have an identical voltage of basically 140 volts there. And we're seeing again 138. Okay, and then between the C and the A, we should also have 138 volts. Looks good, 138.9.
Okay, and then it wants us to look at the voltage between A and neutral, B and neutral, and C and neutral. Okay, so A and neutral, 70 volts. No, 85. 8.5 volts. What am I doing here? Have I messed something up here? You know what? I didn't do that last connection there, guys. I didn't do the X2 to the neutral. So let's do that, and then we'll double check things. Sorry about that. So X2 is supposed to go to ground, but it's also supposed to feed our neutral there, right? So I put X2 to the ground. Let's bring this ground reference to the neutral. This is for this guy, so this is going to tie this to this. Okay, there we go. Okay, let's take a look at the voltage now. There we go, 70 volts. Okay. Now between B and neutral, we should have 70 volts as well. Looks good. Okay, 69.3. And then between C and neutral, let's see what the voltage is. 120? 121 volts. Excellent. So identical to the previous transformer. Okay, next thing we're supposed to do, on page 19 of the student manual, is we're supposed to look at the voltage between the bus bars on the secondary there. So we're supposed to look at A1 and A2. So let's do that now. So A1 and A2. Those guys, we have a 30 degrees phase shift on the first transformer, 210 on the other transformer. So there should be a voltage difference between those two bus. And we're seeing 138 volts. So basically, like they're saying in the answer manual, 140. There's a glare there, sorry. Let's see if we can see it there. Okay, looks good. So there's our 138 between the two A bus. If we look at our B bus, the comparison between B1 and B2, we have, again, 138.8 volts, so identical to what we saw in the A phase. And let's take a look at the C phase and see what difference we have between those guys. Okay, so C1 and C2. We're seeing 242 volts difference between those guys. Okay, so hopefully you're finding like the trick here in that when you're looking at the if you're looking at two different circuits, like in this case we have the Y to delta 30 degree phase shift being compared to the Y to delta 210 degree phase shift. If we take a look at the results there, we're seeing 138 from A to B, and then 138 from B2 to C2, 138 from C2 to A2, right? Then from A to neutral, we saw 69, B to neutral, we saw 69, and then from C to neutral, we're seeing root 3 of 69. So 69 volts times 1.732 gives us 120 volts on the C phase. Now looking at the voltages between the lines, A1 and A2, we're seeing 138, B1 and B2, we're seeing 138, and then C1 and C2, the C phase is having the higher voltage consistently, right, being 120, and it seems like it's always root 3 of whatever the A or B voltage is. So if we take 138 volts, multiply it by 1.732, that gives us the 240 volts between the two C phases. Let's take a look at the diagram here, and let's walk through each one here. So let's start off with from A to A, right? So A1 to A2. So we're finding hopefully the quickest path from one to another. It looks like we're going to be, this is the common connection here with this common ground, right? So we're going to be coming along the A bus, right? Coming up here, and it looks like we are picking up 69 volts here, going to the common ground. Coming from the common ground, we're picking up, again, these voltages are identical, right? So we have 2.8 as our line voltage, 120 volts on the primary, 69 volts on each of our windings there. so picking up another 69 volts before coming back to the voltmeter. So then we have 69 minus negative 69, giving us 138 volts from A1 to A2. Okay, let's just double check that that's the same. Yes, it is. A1 to A2 was 138 volts. Excellent. Okay, so that seems to be working out. You notice I'm doing this quite a little bit faster than the previous time we went through this, because it seems that this is working out with each of the transformers. Let's look at the voltage between B1 and B2. So this voltage right here. Okay, again, common connection here on the neutral. We're coming along this bus. We're coming up to here. Okay, looks like that connection is going to the first transformer, right? Because that first transformer is going from A to B. Then we've got this guy coming over, picking up 69 volts, going to the common ground. From the common ground, we're now coming up. This one has 69 volts as well. And it looks like the quickest path is here to the B phase. So we've picked up 69 volts here. We picked up 69 volts here. So 69 minus the negative 69 again is giving us 138 volts from B1 to B2, which is what we saw on our answer sheet right here. Excellent. Okay, so now we're going to see C1 and C2. We'll see whether that gets to be 240 volts. Okay, now going between C1 and C2. So that's our voltage right here. C1 being here, C2 being the other bus right here. Okay, and let's follow this through and see if we can find a path to this common neutral here. So this right here, let's see. There's probably a number of different paths here. Let's just pick one. So I think previously we went through the B phase. Let's see if that works as well. Is that going to work? So picking up here, coming across down to here, that looks good. Yeah, okay, so looks like that's our path, one of the paths there, right? So from here through both these windings, so picking up 138, coming down here, picking up 69, right? And then going to the common ground. Then that common ground comes up to here. We got to find our way back to the C phase here. So we've got to eventually come to here. So it looks like we're going to pick up, we've got 69 on each of these guys, right? Looks like we're going to pick up 69 here, 138 here, and then back to the C phase there. And then keep in mind that, again, these 69s are not happening. This 69 and the 138 are not happening, right? So remember that we've already done this numerous times, that 69 volts at 0 degrees and 138 at 120 degrees. Now again, those degrees are different, right? Here we have a 30-degree phase shift and a 210. We could do the vector sum, but we know that from previous times we had 120 volts here, and we had 120 volts being the vector sum between 69 and 138 when they're 120 degrees out of phase. So 120 minus a negative 120 gives us 240 volts between those guys. And again, checking our answer here, we have 240 volts between C1 and C2. So I'm not going through the math again with the vector sum between those guys because we've done that numerous times, but it is interesting in that if we want to find this voltage, the previous value is 138 times root 3 ends up giving us 240 volts on the C phase there. All right, let's move on to the next one, guys.
Okay, guys, getting near the end here. So we got, this is page 19 in the student manual and page 23 in the instructor's manual. We're doing the Y delta 30-degree phase shift, grounded Y primary. So the diagram is on the next page. It says connect the circuit shown in figure 1.14. That is found on page 20 of the student manual. So for that guy, it looks like we have all the H2s tied together. So let's start off with that. So all the H2s are going to be tied together. And then this is the grounded primary, right? So all of them are going to be tied together, and then you'll notice that H2 of transformer 2 is bonded to the neutral. Okay, so that's going to the neutral. Where's that going? That's going to the primary, yeah. So that's going to the primary here, right? Then keep in mind we have to jumper this guy out. We could just bring this over here if we wanted to. And it looks like that is bonded to ground. I believe it is, I'm not sure. Let's just make sure. Like, I don't know if this needs to be done, so we'll try that and see if it holds, whether that's needed or not. Then on the feeds there, we have obviously each phase. So A is feeding H1 of transformer 1. B is going to feed H1 of transformer 2. Okay, and then C is going to feed H1 of transformer number 3. Okay, let's see if that holds first. Okay, seems good. Next thing we're going to do is do our secondaries there. So it looks like on the secondary, let's not forget that X2 looks like it is again bonded to ground. So you see transformer 1 has X2 bonded to ground. So let's do that before we forget. Okay, and then it looks like we have X1. This is a delta, right? So X1 is going to go to A. So X1 of the first transformer, transformer 1, feeds the A bus underneath. Okay, then we've got X3 should be going to B. It is. So X3 is feeding the B phase. Okay, then we should have X1 of the next transformer, transformer 2, going to B. Yes, it does. So X1 is feeding the B phase. Then that X3 of that guy should be going to the C phase. Excellent. So X3 feeds the C phase. So A to B, B to C. Now C to A on the last guy. So X1 of transformer 3 feeds C. So X1 feeds the C phase. And then final connection is going to be X3 back to the A phase. Okay, so X3 to the A phase. Beautiful. Let's see if that holds. Looks good. Okay, and now we're doing, if we flip back to page 19, we're looking at connect the circuit, determine the distribution, determine the voltage between lines A1 and B1. Okay, so A1 and B1. So that's on the secondary side. Okay, so let's look at that. Let's grab some conductors here on our meter leads. So before we start with that, let's look at the primary first. Obviously, we've looked at this so many times, but this is going to be 208. Okay, looks good. It's 209 today. And let's look at the voltage on the primary windings here. So we're going to go from H1 to H2. Now that is a Y, so that should be 120 on the phase there. Beautiful, so there's 120. If we lift this ground, does it change anything? No, it doesn't change anything whatsoever. Okay, so not sure if that's required there or not. I'm gonna have to check. So obviously that's 120, and if I go across to each of the primary windings, then we should have 120 on each of our primary windings. So this is the second transformer, 120, and third transformer should be 120. So it's saying here that the answers are, we're expecting 140 volts between A1 and B1 on the secondary side. And that is because we have 120 volts on the primary of this Y to delta transformer. That means that we're going to have 69 volts on each of the X1 to X2 and X2 to X3. And 69 plus 69 is basically 70 plus 70, giving us 140 on the secondary side. So let's check our voltages from A1 to B1 now. So should be 140. Excellent, 138.9. Okay, we'll look at from B to C, should be identical. 140, and then from C to A should be identical at 140. Excellent. Okay, so those are our voltages from A1 to B1, B1 to C1, C1 to A1. Okay, then it says turn off the distribution transformer, disconnect the primary of T1, and turn on the distribution trainer and determine the voltage between lines A1 and B1, B1 and C1, C1 and A1. Okay, so this is going to be an open Y then. And we're removing the primary of transformer number 1. Okay, so primary of transformer 1 is going to be eliminated. So we'll take this guy out, and we'll take this guy out. So removing them completely from the circuit. Okay, so open Y, we should still have, what are they asking for? They're asking still for the secondary voltages there, right? So again, let's take a look at secondary voltages. So we're at 135 from A to C, from A to B. We have 134. And from C to B, we're having 139 there. Okay, so basically the same. There was a little bit of a drop on the A and the B phase, but C phase seems to be identical to what we had before. Let's check our primary voltage here. So we're checking out the voltage between H1 and H2. This should still be 120. Okay, so still 120. And on this guy, we should still have 120 as well. Excellent. So small drop in voltage on the A and the B phase on the secondary side once we've opened that delta there. But aside from that, the C phase was identical. Okay, moving on to the next page, on page 20, do your results demonstrate that it's possible to supply a three-phase load with only 2 transformers? Yes, if you have an open Y, you are able to do that. The issue is that again, you're going to be reducing the amount of power that's available on the secondary side because you've essentially eliminated one of the transformers there. Okay guys, last one, page 21 of the student manual, page 25 of the instructor manual. We're doing delta Y 30-degree phase shift now. So don't go on cruise control, watch the wiring there. Looks like the first transformer, because usually we're doing A to B, B to C, C back to A, right? But taking a look on page 21, we have the wiring for transformer number 1. A is definitely going to H1. But if you take a look at H2 of transformer number 1, it's going to C. Okay, so don't be on cruise control, watch the diagram there. Okay, next one is going to go C to B, so transformer 2 is C to B. So that is C to H1. And then B to H2. Okay, and then on transformer number 3, we have H1 going to B. Okay, and then H2 is going to A. Okay, we know this is going to hold, but let's try it just in case. Okay, just so we know that our primary is good. Okay, now let's look at the secondary now. So this one's a little bit funky. We have X1 going to A. Okay, so X1 of the first transformer is feeding A. Okay, X2 is going to the neutral, and the neutral is going to be grounded. Okay, so we've got X2 going to the neutral, and we're going to bond that neutral to ground. Okay, let's see, X2 of the transformer number 2 is also going to the same point. So X2 of this second transformer here is also going to the neutral. I'm going to go here just so I have that open, take some meter readings. Okay, let's see, X2 of the third transformer is also going to the neutral. Okay, that takes care of all of our X2s. X1 of transformer 1 went to A. X1 of transformer 2 is going to C. So X1 of transformer 2 is going to C. Okay, is that the same phasing as we had above? Yeah, so you'll notice that on transformer 2, H1 was being fed by C. So on transformer 2, X1 is now going to C. If we take a look at transformer number 1, H1 is fed by the A phase, and X1 is feeding the A phase on the secondary. And then on the third transformer, H1 is being fed by B. Okay, so H1 is being fed by B, and so X1 should be going to the B phase. So our final connection here for X1 is going to go to the B phase. Okay, so I'm not sure what voltages we're going to get here. Let's see. I haven't looked at this one yet. So we have a delta. So let's work through this. If we have 2,8 on the line, then we should have 2,8 on the phase, right? So turn on the distribution transformer, determine the voltage between lines A, capital B, capital C, and capital C and capital A. So those are our primary voltages. So again, we have 2,8 here, right? So we've seen this 1,000 times. 2,8's available right here. That's our line voltage. So our phase voltage on the delta should be 2,8 as well. Very nice. Okay. So today we're at 210, 2.9. Okay. Looking at the second transformer, should be identical voltage. Okay, so we're at 209. You'll see, again, I've mentioned this numerous times, but you will find the voltage goes from like 207 to 210 on this floor. There's a big compressor down on the other side of the this floor, and when that compressor turns on, then the voltage sags for the entire floor. So some days we'll have higher voltages than others. Today we're having 209 volts on the primary there, matching phase voltage on the delta, matching with line voltage on the delta there. Excellent. Okay, what are they asking for next? Next thing we're asking for is the secondary voltages. So on the bottom of page 21, they're asking for the voltages from A1, so small case, lowercase, A1 to B1. So let's look at that now, guys. So that's also 2,8 on the secondary side. So we had 2,8 on the primary side, and we also have 2,8 on the secondary side with that Y there. Okay, let's look at see whether the voltage between B and C is identical. So we have 2,8 between those guys. Between B and C, let's see. 2,8, okay, and between C and A, 2,8 as well. Okay, so those are our voltages on the line values of that Y. And then it's asking us, if we flip the page to page 22, it's asking us for the voltage between A1 and neutral. So we'll move this down to the neutral now. Let's move this over so you can see it. So A1 and neutral, if we had 2,8 as the line voltage, we should have 120 as the phase voltage. There we go. So line A to neutral is 120. B to neutral, 120. And C to neutral, 120. Excellent. Okay, so and the only thing you'd also want to be careful of here is just at the end of doing all these connections here, you may find that your students are getting overconfident and they're not turning off the transformer when they're changing meter leads there. So you just have to keep on top of them to make sure that they are keeping safe all the way through to this final project here. Okay, last one. Now we got Y to Y is 0 degrees phase shift. So again, 0 degrees phase shift because we have a Y in the primary and a Y on the secondary. So this diagram, so I am on page 23 of the student manual, 27 of the instructor manual. And looking here, what looks like we have all of our H2s tied together. And then the question is, do you have to ground that neutral there, right? So let's tie those guys together. We've got all of our H2s that need to be tied together to create that star point.
Okay, then that star point is then going to the neutral bus here. Again, could have gone to there if I want to. And then the question is, do you actually need to ground this out? I would say no. I don't think I need to do that. I think that's already internally done. But we'll do it just for good measure. Okay, then looking at the transformer number 1, H1 is being fed by A. Transformer 2 is being fed by B. And the H1 of transformer 3 is being fed by C. Okay, primary is still good. Okay, on the secondary there, we have a Y, and so it looks like all of our X2s are tied together, and that's going to the neutral, and the neutral is being grounded. Okay, so we'll ground the neutral first. Then we'll tie all of our X2s together. Okay, X2s are tied together, and then that's going to feed that neutral bus. Let's move this over so we have a place to take a meter reading. Okay, so X2s are done. X1 on the primary, H1 is fed by A, so X1 is going to A because we have a 0 degrees phase shift, right? So X1 is feeding the A bus here. Okay, then we have X1, second transformer, feeding the B. And then finally, the last connection, we have X1 feeding C there. Beautiful. It holds. Okay, so next thing is they're asking us the voltage between A and B. So those are our line voltages. Well, I mean, we've looked at that so many times, right? So let's take a look at those guys. So we know that it's 2A, right? So 2A, 2A, and 2A. Okay, then it's asking us for the voltage between the lines on the secondary side. Before we do that, let's take a look at the voltage on each of these phases here, right? So if we have 2.8 on the line, then we should have 120 on the phase, right? So H1 to H2 should be 120. And these should all be identical now, right? $120 on the second transformer and 120 on the third transformer. They're not asking us for this, but might as well check it out. Okay, that is going to transfer to the secondary, and our secondary voltage, we have 120 on the center there, which means that we're going to have √3 less. We're going to have 69 volts from X1 to X2. They're asking for the voltage between the lines. So let's do that first, and then we'll look at the phase voltage on the secondary. So between A1 and B1, let's see what we got. So we have 120. So that's our line voltage on the outside of the Y. Between B and C, we should also have 120. And between C and A, we should also have 120. Okay, if that's our line voltage, it's interesting that they didn't ask us for the phase voltage, but phase voltage between these guys should be 69 volts. 69 here on the C phase, 69 on the B phase. Beautiful, and the last meter measurement here should be 69 on the A phase. Excellent. That concludes the transformer trainers from Festo. Thank you very much for sticking through the entire video. Last thing I wanted to highlight, guys, is there are faults at the back here. So if you open up the cabinet, so we'll have to find a place to keep all these keys so that they're readily accessible, but not to the students. And so for each of these guys, there are a number of different faults. So there are 8 different faults, and on page 57 of the instructor manual, number 1 is an open primary on transformer number 1.
Number 2 is an open secondary on transformer number 2. Number 3 is secondary of transformer 3 shorted to ground. Number 4 is line B shorted to ground. Number 5 is open primary on transformer number 4. Number 6 is open secondary on transformer number 5. Number 7 is secondary of transformer 6 shorted to ground. And number 8 is line C2 shorted to ground. So interesting that it doesn't tell you when to use those faults. So we'll have to figure out which of the labs that we're going to put each of these faults on. So that concludes everything that's in the Festo training manual. I find that these should be a really good help to the students to understand the delta Y, open delta. And if you have any other additional labs you'd like to add to here, please let me know. We'll add it onto the OneDrive. We've seen a couple labs where the loads were added on with the light bulbs, but a large number of the labs were done without a physical load. So we may want to drop in some of the light bulbs to show different currents that are happening in the circuit and different voltages on the lighting loads. But so far, these trainers are great, and I think they're really going to add to our existing Hammond transformer trainers.